Hello everyone, welcome to the course on Electrical and Electronics Engineering. In this session, we are going to see Unit 1 under the topic of electric circuits. We are going to discuss about the DC circuits. So the outline of this session is going to be the introduction to basic terminologies in DC circuit. And we are going to understand about active and passive components, and we are going to learn Ohm's law, the network reduction techniques for the series, parallel, and combination of double circuits, and what are the types of DC sources, how to transform them, and how to combine them.
So coming to the basic terminologies used in DC circuit, we know that electrical circuits is broadly classified into direct current circuits and alternating current circuits. In both these DC and AC circuits, we are using many two-terminal elements. So in this table we can see that there are different two terminal elements are mentioned along with its representation. So first we will see about the voltage source, or we can call it as a battery, which is represented by a small line followed by a long vertical line, where the small line represent negative terminal of the battery and longer represent the positive terminal, and same can be represented by using a circle also. When we go for AC circuits, the same voltage source can be represented in the form of circle followed by the signs along with the sine wave, which represents it is using the alternating current. Okay, and the current source, regarding that, if we see it is represented by a circle followed by a arrowhead, okay, which represents the direction of current flow. In both DC and AC circuits it remains the same. When we go for the passive components, the resistor is represented by a straight line followed by a zigzag line, where it starts at the zigzag start at the top head and end at the bottom. Similarly, in AC circuits, when you go for inductor, it is represented as a winding, and a capacitor is represented by a straight line followed by a curved line. Now let us understand the difference between active components and passive components. What do you mean by active component? Active component is an electronic component which is going to supply energy to the circuit, and it has the ability to control the electron flow or the flow of charge. So in all the electronic circuits that we are seeing, it will contain at least one active component. The active components examples are voltage source, current sources, could be a generator, transistor, or diodes. So when you go for passive component, it is an electronic component which will only receive energy. Okay, but whereas active components we saw earlier, it is going to supply the energy, right? Yeah, but the passive component will receive the energy, and it will either dissipate, absorb, or store the energy in the form of electric field, in terms of in capacitors, or magnetic field in case of inductors. So the examples for passive components are resistor, inductor, capacitor, and transformers. Let us see about DC circuit. Here in the figure we can see one battery or voltage source is connected in a series across a resistor, and based on the voltage and resistors, the 3 amperes of current is getting flown here. We will see the relationship between voltage, current, and the resistance in the Ohm's law in the upcoming slide. So this is an example of a simple DC circuit. Here we call a voltage, right? What do you mean by electric voltage? So it is nothing but the potential difference between 2 points, okay, or we can say the amount of energy required to move a positive charge from between these 2 points. The amount of energy required to move the unit charge between these 2 points. The unit of electric voltage is volts. What do you mean by electric current? So it is the flow of electrons, how the electron is getting flown, okay, in the circuit. Its unit is ampere. So there is a difference between conventional current flow and electron flow. Actually, current flow, as we saw here, it flows from positive terminal of the battery to the negative, whereas electron flow is opposite to that of the current flow. Okay.
Now let us see about Ohm's law, which is one of the fundamental law governing the electric circuits. So the statement goes like this: the ratio of potential difference between any two points of a conductor to the current flowing between them is going to be a constant. So that constant we are going to say as R, that is the resistance, provided the physical conditions, for example the temperature, doesn't change. So the Ohm's law we can express in either of these forms. V by I is equal to the constant, that is R, or V equal to IR, or I equal to V by R. So what do you mean by resistance here? Resistance of a conducting material, it is going to oppose the flow of electrons. So it is measured in ohms. Now let us see about electric power. Power is termed as work done in a given amount of time. How much work is done? So it's a product of the voltage and current, or if we substitute the Ohm's law relationship, we get other two formulas for the power in terms of current and resistance I square R, in terms of voltage and resistance V square by R. The unit of power, it's watts. What do you mean by electric energy? Electric energy is a rate at which electrical power is getting consumed. So it's a product of power into time. So power unit is watts, time unit is seconds, or we can take it in hour also. Watt hour or watt seconds is its unit. So based on our understanding of Ohm's law, we will see how to find the equivalent resistance when number of resistors are connected in series manner. So if a number of resistance, so three resistors are connected in series, R1, R2, R3, okay, across the battery, and the current is flowing, right? So how we draw the equivalent circuit? The equivalent circuit is the total resistance here. Okay, we'll replace. Whenever resistors are connected in series, the total resistance is going to be the sum of the individual resistors. Okay, and the current, if I want to find voltage divided by total resistance, we can find the current. And there is a voltage division rule applying here, because across individual resistance, okay, some voltage drop is getting occurred. So it's the voltage drop is not same. So the voltage division technique will help us to find the voltage across the individual resistor. V1 equal to total current into R1, V2 equal to total current I into R2, similarly V3. If I want to find the individual voltage drop, we just V1, if I want to find, it is nothing but total voltage, okay, divided by total resistance into the resistance value for which we are supposed to find the voltage drop. Similarly for the other two voltages. This is the voltage division rule. Now let us see when the resistors are connected in parallel. When the resistors are connected in parallel, the voltage drop remains the same, but the current get divided, because there are three different branches. The total current get divided into I1, I2 and I3, since there are three resistors. And what is the equivalent resistance? So 1 by RT is nothing but 1 by R1 plus 1 by R2 plus 1 by R3. If I have n number, it plus etc. 1 by Rn. Suppose when two resistors are connected in parallel, the equivalent resistance is going to be R1 R2 divided by R1 plus R2. Now let us see about the current division technique, which is applicable to the parallel combination of resistance. So the total current is getting divided between these two resistors, and the individual current, if I want to find, is equal to total current into opposite resistance divided by the total resistance. So here it is I into R2 divided by R1 plus R2. Similarly, for if I want to find current across resistance R2, it is nothing but I into opposite resistance R1 divided by total resistance, which is R1 plus R2. So that can be a series parallel combination also. So in that case, we know the equivalent to find the total resistance. So the R1 is going to be in series with the parallel combination of R2 and R3, and that we call it as RP. RP is nothing but the parallel combination of these, and that we have to sum with R1 to get the total resistance. So let us see how to solve the given problem. For the circuit given here, we are supposed to find the one of the parallel resistor, that is R3. So they have given the total resistance value across the terminal A and B. What is the total resistance? 6 ohm is given. And if we want to find one of the resistor, what we have to do? We have to consider this as equivalent resistance of R4, which is going to be a parallel combination of R1 R3. Okay, so the formula is R1 R3 divided by R1 plus R3. The unknown value is R3, and we know that it has to be connected in series with R2 also. Okay, so if you substitute in this entire equation, RT we know that is total resistance is 6 ohms, R4 is nothing but this parallel combination, plus R2 is given here. Okay, so if we take the terms on the left hand side, constant terms, and if we equate, we get R3 as 2.4 ohms. So we have applied the parallel combination of resistance. Okay, now let us see one more problem where a voltage source with power value is given, and we are supposed to find the resistance in series, but parallel combination they have given, but we don't know what is the total resistance. So to find that, some other values are given. Let's see. The total resistance in this circuit is R1 in series with parallel combination of R2 R3. So this is a formula. So if you substitute the known values R2 and R3, we get this expression, right? And they have given the power and voltage relationship. From that we can find what is the current. Okay, from the current value, by using the Ohm's law, we can find the total resistance, which is nothing but the total voltage divided by total current, which is going to be 6.92. So if we substitute the RT value in this first equation, we get what is the unknown resistance, that is R1. Okay, now let us see one more problem where the resistors are with equal value of R, they are connected. Okay, and what is the value of R when the switch is in open position? Okay, and the battery current is 1 amp, the battery voltage is 5 volt. Okay, let's see when the switch is open position. Okay, we know that here four resistors are connected in parallel, means we know the total resistance formula. 1 by RT is nothing but 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4 also comes to picture. So the equal resistance is going to be R by 4. So the total resistance is a series combination of this resistance R and R divided by 4. And prior to that, we know one more thing, the total resistance value we can find from the voltage and current value, V by I. From the Ohm's law, if we substitute, we get 5 ohms. So if we equate in this expression, okay, we get the value of R, because here the total resistance is 5 ohm, and this R plus R by 4 is 5R by 4. Equate it, we get 4 ohms as the final value.
Now we are going to see the types of DC sources. So there are two sources. One is a voltage and other is a current source. And both of them can have two types. One is a ideal and other one is a practical. There can be an ideal voltage source, practical voltage source, similarly ideal current source and practical current source. We are going to see all these things now. What do you mean by ideal voltage source? So ideal voltage source is a one. Here Vs is the ideal voltage source. It is going to maintain the constant voltage regardless of the current drawn. Okay, whatever current is going across the load, regardless of that, it is going to maintain the constant voltage, output voltage. That output voltage is going to be the supply voltage, right? So what is the meaning? It has zero internal resistance, right? When we go for practical voltage source, it has a small internal resistance associated with it, which is connected in series. That is called RINT. So as the load current increases, what happens? It will not be the same as the ideal voltage source, but the voltage, output voltage, what happens? Terminal voltage, it's good drop. Okay, because of this internal resistance. So the output voltage V out going to be Vs supply voltage minus the voltage across the load, IL into R into. Mean by ideal current source? Ideal current source is nothing but a constant current source that supplies the same current regardless of the voltage across it. Okay, and the load that is going to be connected to it. So what is the meaning? It has an infinite internal resistance. Since the current is supplied by the ideal source is going to be constant, the voltage across it depends on the value of the load. Okay, so in reality, we can see that all the current source has some drooping characteristics due to small internal resistance. Here also in practical case, there is a small internal resistance that is associated with which is connected in parallel manner. So a practical current source has some finite internal resistance due to which the current delivered right to the circuit will not be constant. It drops off. Right. Now we will see the transformation of DC sources. So a source can be converted to a current source. How? We know that a practical voltage source has some small internal resistance that is associated with it, which is connected in series manner. This can be converted into practical current source is connected in parallel with the small internal resistance, where the Is is going to be Vs by R int by the Ohm's law. Similarly, we can convert the current source to the voltage source by making the reverse of the above. A voltage source, we always know that it has internal resistance connected in series, whereas a current source has internal resistance, it is connected in parallel with it. And here Vs supply voltage is going to be Is into R int. Now we are going to see the combination of DC sources. So till now we have seen what is ideal voltage source, ideal current source, practical voltage source, practical current source, then how to transform the sources. Now we are going to see the combination of them. If two voltage sources are connected in series, so V1 and V2 are connected in series through the resistance R1 and R2. So what happens to the total voltage? It is going to be the sum. So we know that the longer terminal is positive, smaller is a negative, here positive, negative. So it's going to be V1 plus V2. And the total resistance by Ohm's law, it's going to be the sum of the internal resistance. And we know when the resistance are connected in series, it is going to be the individual sum. Then here is another case where there is a change in the second voltage. So terminal, if you see, it's connected in a reverse. So if V1 is greater, the total voltage is going to be V1 minus V2, but total resistance remains the same. And in this case, if V2 is larger, then we have to write the total voltage as V2 minus V1. But the total resistance remains the same as the previous. Now we are going to see when the two current sources are connected in parallel. If it is connected in parallel, what happens? The total current is going to be the sum of individual current, but the total resistance is going to be the parallel combination. If two resistance are connected in parallel, we know that the total resistance is going to be R1 into R2 divided by R1 plus R2. Similarly, in the previous case, direction of currents are same, right? Now let us going to see I1 is larger than I2 means the total current is going to be I1 minus I2. Total resistance remains the same. If I2 is larger than I1, in this case, the total current is going to be I2 minus I1. The total resistance remains going to be same. Now we are going to see the other case when two voltage sources are connected in parallel. So this we can't find the total voltage or resistance directly, but we have to do the source transformation, convert this voltage source into current source. Okay, that is connected voltage connected with the series resistance mean it has to be replaced by a current source in parallel with the resistance. Similarly, this V2 also. Then we can find the total current, and combination to parallel combination is going to be RT. That can be converted into. So we know that the source transformation happening here. Similarly, the other case, if current sources are connected in
parallel, we can't find the total current or resistance immediately. We have to convert into the other sources. Okay, current has to be converted into voltage source in series with the resistance. This parallel combination has to be made as a series. Then we have to find the overall value. Hope you understood. Thank you.